Hi, it's time for another math easy solution. To discuss further into conic sections in polar coordinates, and now look at further at the theorem and prove that it's applicable for ellipses as well. In my earlier video, I went over on parabolas as well as a summary of the Unified Theorem in earlier videos, so check those out. So let's just jump right in. So in my previous video, I covered the proof of the Unified Theorem for conic sections in regards to the parabola, and in this video I will prove it is indeed applicable for ellipses. So first of all, recall the conventional definition of an ellipse and its formulation in standard Cartesian or rectangular coordinates. So make sure to watch those, that video as well in my earlier video. I'll put that earlier videos. I'll put that in the link in the description below. So let's look at the definition. So an ellipse is the set of points in a plane, the sum of whose distances from two fixed points f1 and f2 is a constant as shown below, and this is the conventional definition. So here is the set of all the points in this ellipse type shape, and then as you can see here, if there's two foci, f1 and f2, the distance from here from f1 to p added to the distance from p to f2, so that the sum of the distances is always going to be constant. So anywhere you go here, it's going to be the same thing. You go here, it's going to be the same thing. So it's constant, and that shape you end up getting is an ellipse. So that's the definition. And then also recall the equation of an horizontal or of a horizontal ellipse in standard form, which I covered in my earlier video as well. So once you derive the Cartesian equation for it, a standard one, it looks like this. So x squared over a squared plus y squared over b squared equals 1, where a is greater than or equal to b and b is greater than 0. So just chose those as positive constants. And then there's the foci is at plus or minus c and 0, where c is equal to a squared minus b squared, and this was from the definition of b squared equal to a squared minus c squared in the derivation, so make sure to watch out. And the vertices are at plus or minus a and 0, and the shape looks something like this. So those are the vertices, negative a 0, this is a and 0, and there's the foci f1 and f2 across there. And then the b is on the vertical side of this compressed ellipse. And also note the relation between a, b, and c. A is a squared equals b squared plus c squared using Pythagoras, and just rearranging that formula above. So it looks like this triangle that extends from the top to the focus like that. It's very interesting stuff like that indeed. So now let's recap on the Unified Theorem for conics, conic sections, which I covered in my earlier videos. So here is the theorem again, just to recap. Let f be a fixed point called the focus, and L be a fixed line called the directrix in a plane, and let E be a fixed positive number called the eccentricity. The set of all points P in the plane such that then the distance right here, PF, divided by PL equals to E. That is the ratio of the distance from F to the distance from L is the constant E. Yeah, so the distance, so we're, instead of just dealing with the summation being constant here, what we do is we look at the distance from one focus to the ellipse divided by, or the conic divided by, the distance to a fixed line called the directrix. Again, recall from my earlier video. So the theorem states that the set of all points here where E is a constant is a conic section, and the conic is an ellipse if E is less than 1, and a parabola if E equals to 1, and a hyperbola if E is greater than 1. And I already proved it for parabolas in my earlier video, so check that out. And MES note, the eccentricity is always positive since it is just a ratio of the distances which are taken to be positive. And I'll prove this theorem for hyperbolas in a later video, so stay tuned for that. And here's again illustration on recap on it. So it looks something like this. So here's how the definition looks like. There's the set of all points over there in this this curve like that, and then there's the directrix across there. There's the fixed line L. There is the focus F. So distance from the focus to the set of all points is going to be PF, and then PL is distance from P to the directrix L. So, and then we take the ratio PF over PL equals to E, and if it's constant, it's a conic section. So I've already proved it for parabolas if E equals 1. Now we'll look at E is less than 1. So also recall from recall that the motivation behind the above theorem is that it can be written in a simple formula when using polar coordinates and setting the focus at the origin or pole. So here's again a recap on the theorem in terms of a simple polar equation. which I covered in more detail in my earlier videos as well. So theorem and simple polar equation. So a polar equation of the form r equals e times d divided by 1 plus or minus e cosine theta, or r equals e times d divided by 1 plus or minus e sine theta. So yeah, plus or minus, and instead of the cosine we go a sine. That's for vertically opening up conics. So these formulas or formula in any of these forms represents a conic section with eccentricity e and the focus at the origin. The conic is an ellipse if e is less than 1, a parabola if e equals 1, or a hyperbola if e is greater than 1, and then the following figures illustrate the different polar equations for various conics. So r equals ed divided by 1 plus e cosine theta, as if x equals to d. The directrix is d distance from f on the positive side. If it's on the negative, we'll have a negative e cosine theta there. Then if it's on the vertical like that, y equals to d, we have plus e sine theta. And then here, if it's minus y equals minus d, then what we have is the minus and sine theta. So again, I proved these conditions in my earlier videos, so check that out. And now let's look at the proof of the unified conic theorem for an ellipse where e is, for the case e is less than 1, to prove that it is in fact the case. So let's first look at when just e is not equal 0 in general, and then see what we can get, because I'll set up the equations for this. In the later videos, I'll carry off where I finish in the middle part of this video, which I'll derive a formula. Then in the later video, we'll just start from there and prove it for parabolas. For hyperbolas when e is greater than 0. But here we'll just look at it in general. So now let us take, let us place the focus at the origin and the directrix parallel to the y-axis and d units to the right. In other words, we want to set up something that looks like this over there. Just be easier for derivation. So thus the directrix has equation x equals to d and is perpendicular to the polar axis like that. So x equals to d is going to be parallel to the y-axis. So let's just draw this out. Alright, so what we have here is the y and the x-axis like that. Let's make this a bit better. And this is the y, this is the x. So let's say this is the point F like that. So we set the focus over there, and also this is going to be our polar axis, as I showed in my earlier videos, is just by convention is a positive x-axis. This is for polar coordinates. And now what I'll do is I'll draw the directrix like this. This is going to be L, and this is also, this equation is going to be, well, x equals to d, and this is the directrix like that. And this distance is d from the right. Or d to the right of f, the focus, which is at the origin. And let's say the set of all points is going to look something like this. Draw this a bit better. So the conic section is going to look something like this. And let's say there's a point here, and I'll call this P, and as coordinates in polar coordinates are theta, as well as in Cartesian it's going to be x, y, like that. So r theta and x, y for Cartesian. This is for polar. And now what I could do is, well, we could draw the angles and the coordinates in polar coordinates. So if you scroll this over from the origin or the pole, this is going to be a distance r in polar units, like this, or polar coordinates. So r, and then it has an angle theta like that. So that is in polar coordinates there. And now the correlating Cartesian connection is going to be like this. It's going to be the vertical side is going to be y. So recall as well that y, this just equals to, well, r sine theta. And this coordinates here, I just fixed up the conic section just to make it a bit easier to put this inside. Just move it over there so you could write this inside. And again, recall, this is just from from trigonometry. From the definition of sine theta is just going to be y over r, or opposite over hypotenuse. And likewise, for the x coordinate here is going to be x. This equals to, again, r cosine theta, because cosine theta by trigonometry is just going to be equal to, by definition, x over r, and then just move the r onto this side, get x, or adjacent over hypotenuse. Alright, so now that we have this, what we could do is, well, apply the theorem above here. So we want to get the distance from P to F and then distance from P to L, and then apply the ratio PF over PL and set it equal to a constant, call that E, or the eccentricity. So we can see here the PF is going to be, well, from P to F here. The focus is the origin right there. And this distance, I'm going to draw this in blue like this. This is going to go from there to here. This is going to be our PF. Let's write this down. This is going to be PF like this. And as you can see, PF is just going to be equal to R there. That's just based on the polar coordinate there. And now the PL is going to be from here all the way to across there. This is our distance PL like that. But we can easily see what this one is. Well, we know that the overall distance here is D. This is going to be D like that. Now this distance from here to here, that's just X, or just R cosine theta. And then basically what we could do is to take the PL, I'll shift it down over here, this line, like this, and draw it all the way across here. This is going to be our PL. This just equals to D minus, so we just subtract this full distance, or subtract this from this distance here. So D minus R cosine theta. So that is a distance there. And then we could just apply the theorem or the ratio to PF over PL, set that equal to constant E, like that. And there is our little theorem, or just application of the theorem there. And now what we could do is, well, apply just the mathematics and the theorem to obtain a formula to describe all this in a useful term. So if the point P has polar coordinates R theta as shown above there, we see from the figure above that, well, PF equals to R. So PF equals to R, and also we have over here PL equals to D minus R cosine theta. So I'll write, and PL equals to D minus R cosine theta, like this. So thus what we have is thus the condition of the theorem. So the condition, and I'll write this condition we have is PF, the ratio, set equals to a constant PF over PL equals to E, or we can do is just move this over like this and get PF equals to E times it by PL. So then this condition becomes now, and we'll write this in polar coordinates, this becomes R, PF is R, equals to, and then PL is equal to D minus R cosine theta. So E times it by D minus R cosine theta, like that, and circle this. And now what we could do is, well, if we square both sides of this polar equation and convert to rectangular coordinates or Cartesian, what we get is, and before I get to that, so we want to make a MES note here. So we do this, so we square both sides and convert to rectangular coordinates. We do this because the Pythagorean theorem relates, relates the polar to Cartesian coordinates. And again, this is in order to connect back to the conventional definition of an ellipse or conic section in general, which was in the rectangular or Cartesian coordinates as illustrated at the start of this video. So what we'll have is, if we square this right there, so we'll have R squared equals to E. I'll square this whole thing. Now it's going to be like this: E D minus R cosine theta, and then squared. So we square this and we want to convert into the Cartesian. So remember, R cosine theta is just X, so this is just X like that. And then when we square this right side is going to be E squared D minus R cosine, or just D minus X like this, and then all squared like that. And then also now recall the Pythagorean theorem. So recall Pythagorean theorem like this. Pythagorean theorem for the connection between the polar coordinates and the Cartesian. So we have R, this is the X and Y. So remember, R squared equals X squared plus Y squared, just using Pythagorean theorem there. Here, let's write it down. So R squared equals to X squared plus Y squared. So then we could bring this down here and get over here. So thus we have r squared equals to x squared plus y squared, which equals to this over there, e squared d minus x squared. Or better yet, just expand this out on the right side, so we can expand it, so d minus x times it by d minus x, like that. And then we could write this down, and then this is going to be, well, equal to e squared, and expanding this, so d times d is going to be d squared, and then d times x can be negative, or this is a d times negative x, so negative dx, like that. Then negative x times d is going to be negative x times d, that's going to be, again, dx, so 2, just add those up. And then minus x times minus x is going to be positive x squared, like that. And now what we can do is just multiply this inside, so we just get e squared d squared minus 2d e squared x plus, and then here's going to be e squared x squared, and then bring that down, it's going to be equal to x squared plus y squared. And now whenever we deal with this, especially for conics, what we want to do is move all of the similar variables, or the x and the x squareds, all together. So we want to move this all onto one side, onto this side, and then complete this square, as I showed in my earlier video, just so we can write everything in terms of just an x variable and a y variable, as opposed to having an x, an x, an x, and a y, so multiple ones. We just want one of each. So, as done in my earlier videos, and you could learn more about completing the square, what we could do is just, I'm going to bring this over, so this is e squared x squared. I'm going to factor out the x squared, so what we get here is an x squared. I'll just write that first, actually. When we factor that out, it's going to be a plus. Actually, I'll just write that down first. So x squared, factoring out the 1 plus e squared. Actually, it's minus now, so it's minus. So we move this over, it's going to be minus. And you could see here, multiply this x squared inside, it's going to be x squared minus x squared, e squared's over there. And this one's going to be minus, it's going to be positive, so it's going to be plus 2d e squared x. And then we have this y squared plus y squared equals to now e squared d squared. And now what I'm going to do is I'm going to get rid of this coefficient in front of the x squared, so there's 1 minus e squared. I'm going to factor that out as well, so I'm going to go 1 minus e squared like this. I'm going to factor it out of both of these, so that what we end up having is, just to set up for the completing the square, so what we get is an x squared. So we're factoring out, this is going to be plus 2d e squared over 1 minus e squared. So because of, as you can see, we multiply this inside, it's going to be 1 minus e squared times x squared, and then the 1 minus e squareds cancel, and we'll just get this 2dx, and put an x there. So we just factor it out, just divide it by it, and take it up. And this is going to be plus y squared equals to e d squared. And again, the reason we want to do this is because we want to, over here, we want to complete the square, or CTS. And now if you recall completing the square, basically the idea is to recall completing the square like this. So recall that what we want is, I'm going to write x plus, I'm going to just use k because we're going to need it. We're going to need a or c later, because I usually use just a. But anyway, so let's say we have x plus k squared. K is the constant, and so what we want is something like that, written in with this form like that. So when we expand this, is going to be x plus k, and then times it by x plus k. So expand this out, this is going to be x squared, and then x times k is going to be plus kx, and then k times x, it's going to be another kx, so add up those with 2. K times k is going to be k squared, like that. So now the idea is we want this is going to be similar to this x squared plus 2kx, and then separate for this one here. So I'm going to move this over like this and rearrange everything. So I'm going to rearrange it and then put this over to that side all the way there. So what we have is an x squared plus 2kx is going to be equal to this x plus k squared. So in other words, we're completing the square, and then minus this k squared there. So this is what we want. So we want this so that there's only one x. So remember, we go from 2 x's, so 2 x's, so like that's right, 2 let's write 2 x's like that. And now we have 1x. This is the whole idea of completing the square. And this is 1x. Very, very interesting stuff like this. So this is what we want. This is some fascinating stuff. So in other words, we want this part here, and I'll scroll this all the way. So we want to complete this square, bring it down, and we want this over there. So let's just do that. So thus, in our case, what we end up having is thus, in our case, we're going to set this part here equal to this x plus k squared minus k, minus k squared. So we have, I'll write this whole one down, x squared. So we have x squared plus 2e, was it de squared, de squared over 1 minus e squared x like this. So we want this equals to this part right here, x plus k squared minus k squared. And the only way we could do this is if, well, we set k equals to this part here. So then this part minus the 2, so this whole thing is going to be, well, 2k. So thus k equals to, it's going to be de, because we want to make it look exactly like this, 2k x like that. Now let's write it here as well. This can be x squared plus 2kx like that. So this is 2d, I mean this is going to be k is going to be de squared 1 minus e squared like that. And then the k squared is going to be, well, the square of that. This is just going to be d squared e to the 4 1 minus e squared. It's all squared like that. And so thus what we have is, and I'll bring this down, so this is going to be equals to, so x squared plus 2 de squared 1 minus e squared x, completing the square, we end up getting is x plus k, which is de squared 1 minus e squared. So yeah, a lot of algebra just to prove that it is in fact an ellipse in Cartesian. So what do we have now? Then k squared is just this. It's going to be d squared e to the 4 1 minus e squared all squared. And now what we could do is, well, box this out. So we finally have that. And now finally we can write this whole thing, complete the square, plug that in, and we'll write here, and finally what we get is, the formula above, 1 minus e squared. So right here, 1 minus e squared x squared, I'll just write this whole thing down. So 1 minus e squared x squared plus 2 d e squared, that's this part, 1 minus e squared x plus y squared is equal to, on the right side, is going to be e squared d squared. E squared d squared. So this whole equation becomes, and what this becomes is, and we could write this and replace it with that. So this goes to over there. So we get now 1 minus e squared like this, and then we get a giant formula. This is going to be x plus d e squared 1 minus e squared all squared like that, minus d squared e to the 4 1 minus e squared squared like that, plus y squared equals to e squared d squared. And now what we could do is, we'll multiply this out. So what we get is a 1 minus e squared x plus d e squared 1 minus e squared. It's all squared, and then minus here the 2 will cancel there. So d squared e to the 4 1 minus e squared, and then we have plus y squared, because the 2 just cancels with this, it's the exact same one, equals to e squared d squared. And now what we can do is move this over to there, so add it onto that side. So what we get is, here is a 1 minus e squared x plus d e squared 1 minus e squared all squared. Right, this is a bigger bracket like that. And then, yeah, plus y squared, and bring it over to this side. I'll put this one in front, of it, just because it's has a denominator like that. And I'll show you, because we're going to add up and use common denominator. So e to the squared plus e d squared. So now what I'm going to do is I'm going to multiply this side here. I'm just going to add these up quickly. So I'm going to multiply it by the common denominator, 1 minus e squared over 1 minus e squared. So we're not changing anything. And then multiply this out and have a common denominator. So this equals to d squared e to the 4 plus, and then this multiplies out, so this is going to be e squared d squared minus e squared, this is going to be e4 d squared, like that, and then divide this by 1 minus e squared, like that. Alright, and as you can see here, this is just going to cancel. So this is d squared, e4, d squared, this is e4, cancels, and we're left with here is going to be equal to e squared, or I'll just write it in front, d squared, e squared, just to use a more consistent approach. We're going to put the e on the right side, d on the left. So we have 1 minus e squared, like that. And then we can just bring this down here. It's going to be a 1 minus e squared, and then x plus d e squared 1 minus e squared all squared plus y squared. And now what I want to do is get rid of this one, so I'm going to divide everything by 1 minus e squared. Just want to make this in the regular conic formula, or ellipse, or hyperbola. So we have now is going to be divide both sides by 1 minus e squared divided by 1 minus e squared. So then this would cancel. So we're left with x plus d e squared 1 minus e squared plus y squared, and then we have this 1 minus e squared, like that. And on this right side, this is going to be just, well, power of 2. So now we have a d squared, e squared, and then we have a 1 minus e squared. So now that we have this, and finally what I'm going to do is, yeah, well, my calculus book stops here and does some other stuff, but what I'm going to do is I'm going to divide, well, everything again. Divide both sides by the right side here, so d squared, e squared, 1 minus e squared, so that what we end up having is we get a formula that looks like this: x plus d e squared 1 minus e squared over d squared e squared 1 minus e squared all squared, like that, plus y squared. And then this one here, we're dividing this out. Since this one's at the top of this one's going to cancel there. I'll just write that for completeness sake. This is going to be 1 minus e squared, and then divided by, this is going to be d squared e squared over 1 minus e squared equals to, well, 1. Because we're just dividing it all out. This would cancel with this part there, with one of them, with a 2. So then what we end up getting is, finally, this is extremely tedious and a lot of algebra, but pretty fun nonetheless if you're following along. Let's write this down again: d squared e squared 1 minus e squared, and then plus, like this, plus the y squared over the d squared e squared over just 1 minus e squared, like that, and this equals to, well, 1. So this, notice how this looks like a conic section, or a hyperbola, or an ellipse. And yeah, that's because if you look at these are all just constants here, and they look just like a typical ellipse or hyperbola. But in fact, now let's finally look at for an ellipse when e is less than 1. So if e is less than 1, we recognize that the above equation is just the equation of an ellipse, and this is because if e is less than 1, then what we have is, then I'll just write then, well, if you square both sides, you just get e squared is less than 1 squared, just equals to 1. And what I'm doing now is move this over to this side. So what we get is 0 is less than 1 minus e squared. In other words, this is negative. So 1 minus e squared is negative. Actually, I mean positive, not negative. This is greater than 0. this is positive, like this, my bad. So this is positive, not negative. So if this is positive, then, well, we could replace this all with a specific set of constants and square them, so we don't need to worry about being positive or negative because it's always positive there. So 1 minus e squared is always going to be positive. It's always less than 1. As you can see, e squared is always going to be less than 1. 1 minus a number less than itself, so it'll give me positive. So what we'll do now is set a squared to make it look like the other one. This one's going to be, well, d squared. I'm going to make this one a squared. So d squared e squared 1 minus e squared squared. So that's this one here is our a, like that. This is going to be our b squared. This is a squared. And here what I'm going to do is I'm going to set this as negative h, because this is standard shifted conics, and I'll explain that in a bit. So I'm going to set this one like this, and then I'm going to set b squared equals to this part here, d squared e squared, d squared e squared, and then 1 minus e squared, like this. And then finally I'm going to go negative h equals to this d squared, d e squared 1 minus e squared. So d e squared 1 minus e squared. I'll set that as negative h. And note here, I'll write here, note negative h is greater than 0 because this is always going to be positive. d e squared 1 minus e squared is always greater than 0, as shown above there. So thus we have h is less than 0, so h is going to be negative there. Just put a little notes. Yeah, my calculus book just uses negative h over there. So what we end up having is, actually before I write the equation, I just want to make another note here. Note, as you can see how b squared relates to a squared, this one's just going to be, well, b squared is simply equal to a squared multiplied by 1 minus e squared. This one is just, or divided by, like that. So a squared is just b squared divided by 1 minus e squared. Or also write b squared equals to, this is going to be 1 minus e squared and then a squared. So when we multiply this out, this cancels. We just get this one there. Let's put another note like that. And now I'll make again another note, as I just stated earlier. MES note, we defined negative h because the standard shifted conics formula includes the term x minus h squared, like that. So just write it like that. So thus, in fact, it is of the form, so now finally put this all together, it is the form of a shifted ellipse with a center at h 0. Note that h is less than 0 via our derivation. So when you have this x minus h, and again, this is how it's going to look like. So the top part's going to be negative h. This is going to be a squared, this b squared. So all we get is a x minus h over, so I'll just write x minus h squared, x minus h squared over a squared plus y squared over b squared equals to 1. And this is, and yeah, this is just an ellipse, a shifted ellipse in Cartesian coordinates. And this folks is hashtag amazing. Absolutely amazing. All that algebra, all that polar coordinates going all the way over to here, and that theorem does in fact prove that it is applicable for ellipses when e is less than 1. And now if you were to graph this out, it's going to look something like this. Here's the shifted ellipse. This is the x, this is the y. So the focus is at the point F like this. And also remember the directrix is a distance d. This is going to be our L. This is our x equals to d. This is our directrix, like this. And then it's going to look something like this. So now if you draw this in Cartesian, it's going to be where the center of it is going to be shifted by h. So it's going to be shifted, instead of, I'll just write this as h here. Like here is the center is going to be somewhere here. I'll write this as h. And again, note h is going to be negative because we set negative h. Yeah, we set negative h as positive. Again, this is my calculus book using it like that convention, but I probably would have done something different. But anyways, just following it. So this is going to be at h, and I'll just write here and note h is less than 0. Just put a little bracket there. And if this is the center of the ellipse, it's going to look something like this. If that's the focus, we're going to have another focus somewhere around here in Cartesian in Cartesian coordinates, it's going to look something like this. And I'll write this over here. This is going to be, well, that's going to be our first focus, F1. This is F2. But in the unified theorem, we just need one. But this one, we're going to have two. And what I'll show you now is, if we recall now that the foci of an ellipse, by conventional definition, are at a distance c from the center, such that, and I'll just scroll all the way back up to show it from my just recap part of the video. So recall that c is going to be distance across from the center of it. It's going to be plus or minus c and 0, so distance c, like that. And also where c squared equals a squared minus b squared. So that is the relation between c and d, and I'll show you it's actually the same thing for even unified theorem. So what we'll do with our distance c, so we have is c squared equals to a squared minus b squared. And now if we apply what we've set them here, so a squared equals to d squared, e squared, 1 minus e squared, squared, like that. So d squared, e squared, 1 minus e squared, squared, minus, and then the b1 is just going to be e squared, like this, 1 minus e squared. And again, now if we want to just combine these together or subtract them, we got to get the common denominator. So I'm going to multiply top and bottom by 1 minus e squared over 1 minus e squared, so it gets the square there. And then what we'll end up having is d squared minus e squared. Multiply this inside, we're going to have to subtract d squared e squared, and then we're going to have the plus, it's going to be negative plus. Now we have d squared e to the 4, like this, and this is not minus, this is just d squared e squared, like that. So yeah, my mistake there. So now we divide this by 1 minus e squared all squared, and then as you can see here, this cancels with this, and we're just left with this d squared e4. So this equals to d squared e4, 1 minus e squared squared, like that, and this equals to c squared. So now what we'll do is we'll square both sides, so thus c is equal to plus or minus square root, we're going to square root both sides, not square, so square root, so this can be d squared e4, so plus or minus, and then 1 minus e squared squared. But now we want c as positive, just it's by convention, always picking the positive, so we just pick it as positive. This equals to now, and I'll just write this down, so c equals to, put an arrow, c equals to, this is going to be, that d is going to cancel there, so d, and then we have e squared, and then this 2 goes away, 1 minus e squared, like that. So this is what we have. But notice what we have here. This is c is equal to this, d squared, d e squared, 1 minus e squared. If we scroll all the way up, what do we have here? That's just negative h there. So that is in fact this negative h, d e squared, 1 minus e squared. So this equals to negative h. Unreal. And this is another hashtag amazing part as well. Okay, this is pretty amazing stuff here. So what this means is the distance is at a negative h, and remember that negative h is positive. So this means that this distance is going to be at a distance negative h from the focus. So in other words, the focus of the unified theorem is the same as the focus for the conventional definition. So this is going to be negative h distance. And again, recall negative h is greater than 0. So that's just an absolute value distance there. And likewise from here to here is going to be also negative h, like that. Very, very fascinating stuff here. And now let's go further. Yeah, so basically this again, this confirms that the focus as defined in the above theorem means the same as the focus defined conventionally for ellipses as shown in my earlier video. Absolutely fascinating stuff, and described above. Also, we can see that the eccentricity can be written in terms of c and a. So what we'll do now is we look at the a squared formula. That's right here. So we want to write c, we want to write e, c, and a all together. So I'm going to write this a squared over there. So if we start off with the a squared, so in there, so we have a squared equals to d squared e squared 1 minus e squared all squared. So that is our a squared, and then we have this c squared from above. C equals to e squared d 1 minus e squared. What we'll do now is if we just square this side, both of these, we have square root both sides. So we get a equals to plus or minus square root d squared e squared 1 minus e squared squared, and again take the positive because we want all, by convention, all the constants positive. So we get the positive. This equals to, write a better positive like this, minus, and then take this. So this becomes d e over 1 minus e squared. And this goes away. So in other words, this is just going to be equal to, well, only difference here is there's a e squared there. That's the only difference. So this is ed or de 1 minus e squared. I just have these mixed up around. But anyways, this is going to be, well, equals to c divided by e. That's all it is. This equals to, well, a times it by e, like that. So very, very fascinating stuff. So in other words, what we have is, yeah, just write this as a like that equals a, and move it over here a, and then we can move this e there, and then move the a to this side. So that's what we could do there. So in other words, we get e equals to c over a. So the eccentricity is equal to c, divided by a, where c is the distance to the foci, and a is the term where you're squaring and dividing it by dividing it into the x component of the ellipse formula. And here I'll be going over in a later video, just make a note, I'll be going over how the eccentricity affects the shape of the ellipse, and hyperbolas also, once I do the proof for it in later videos, so stay tuned. Also, MES note, we could also find the above eccentricity formula as follows. Instead of it doing it like this, what we could have done was, well, if we scroll back up, we know that c squared equals a squared minus b squared. So we could just write this as, just for reference, c squared equals a squared minus b squared. But we also know from above, as I showed you, b squared is just equal to 1 minus e squared times a squared. So there is our three variables there. We have c, we have a, and we have e. So this equals to a squared minus 1 minus e squared a squared. And again, this whole thing is our b squared. So we got rid of the b, and now we just have this, and then we factor out the a squared. This equals to a squared 1 minus 1 minus be positive e squared. Like that, this cancels, and we're just left with an a squared, e squared, and then 1 minus, then we have c there, so this c squared. And now we can just square both sides, so what we get is a, squared, so we have c equals to plus or minus square root a squared e squared. In other words, we have basically those, get rid of it. We only want the positive side of it. We want positive c for convention. So if c equals to a e, and then move the a over to this side, what we get is e equals to c over a. Absolutely fascinating stuff. So we can do it this way there, and easier than actually putting in the variables there, but you can just do that way. But either way, it's pretty, it's all the same. But yeah, I just wanted to show that you could do it multiple ways. Anyways, I'll go over the proof that a hyperbola is represented by the unified theorem when e is greater than 1 in a later video, so stay tuned for that. And that is all for today. If you follow along this pretty algebra intensive mind-bending calculations, or just formulations and moving things all around and just manipulating a bunch of terms and whatnot, completing the square using Pythagorean theorem, polar coordinates, Cartesian, and whatnot. But yeah, pretty fun if you follow along and been able to catch up on it. Anyways, all for today. Hopefully you'll learn from this pretty intense video, and like always, you could download these exact notes in a link in the description below, as well as viewing these notes on Steam. And follow me at MES. And also make sure to check out my cool math and science forums, as well as my Discord chat room, and post any cool math or science related stuff you find. Anyways, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.